Molecular orbital theory is particularly useful in explaining the bonding of benzene, which you'll know from your aromatic chemistry unit did cause chemists a great deal of problems, and it was explained by a delocalized model. But how exactly does that model work? The original structure of benzene was thought to contain alternating single and double bonds, but this model was revised, and we now understand benzene to have a delocalized system of 6 electrons, and those 6 electrons are spread above and below the sigma framework. But how do those pi orbitals interact with our new understanding of molecular orbital theory? Well, first things first, let's just look at that benzene sigma framework. Obviously, each carbon atom will have formed sp2 hybrid orbitals in order to then form molecular orbitals in forming the ring and also the bond with hydrogen. So each of those carbon atoms has formed 3 sigma molecular orbitals. Corresponding, there will of course be anti-bonding orbitals, but they will not be occupied. We just have the molecular bonding orbitals occupied. This picture is trying to show the atomic p orbitals of each carbon atom that are going to form the delocalized system. And as you'll be aware, they can be in 2 phases. So one half is going to be positive, the other half is going to be negative. I've just currently shown this model to have all the p atomic orbitals in the same configuration, in that the positive phase is above the ring and the negative phase is below the ring. However, there's nothing to actually stop the orbitals being configured in an alternative way, and this diagram shows the nearest atomic p orbitals being a negative phase above the ring and a positive phase below, which is the opposite to the 3 at the back of the ring. And there are a number of combinations that we can look at. So in a similar way where we could form bonding and anti-bonding orbitals in a pi bond, we can equally form bonding and anti-bonding molecular orbitals when we combine these 6 p orbitals to form those molecular orbitals. So in order to make the diagrams a little bit easier for us to see, I'm just going to show the phase of the orbitals looking from above. So this diagram would represent the phase that we initially saw, with all the orbitals being in the same configuration. So this is your first molecular orbital, which is spread over the whole of the ring, with a positive phase across and a negative phase below. We then have 2 further pi bonding molecular orbitals shown by this configuration. Now the green line represents a node. That's where there isn't any electron density because the phase changes between positive and negative. So we can see that in the left hand side diagram we have got bonding between these orbitals and these orbitals to form the molecular orbital, and this molecular orbital would have electron density here and here. So those are of the same energy and they are considered to be bonding molecular orbitals, but of a higher energy than the first one we saw. That gives us our 3 bonding molecular orbitals. Remember, we started originally with 6p orbitals, so we're going to form 6 molecular orbitals, and therefore we have 3 bonding and now are 3 anti-bonding. So these are our first anti-bonding orbitals, and we have 2 of them here. And you'll notice that for these we have 2 nodes where we will not find any electron density, and those are represented by the green lines. As I said, these are considered to be anti-bonding, so they are of higher energy than the original p-orbitals that combined to produce them. And finally is our highest energy antibonding orbital, and you can see the original p orbitals would have had alternating phases. There are three nodes across the molecule, which produces the highest energy antibonding molecular orbital. This diagram represents how our 6 electrons are arranged in benzene's molecular orbitals. So we started with our 6 2p atomic orbitals, and we have formed 6 molecular pi orbitals. And we have our 1 pi, which is bonding. We have two 2 pi's, which are again bonding, and two 3 pi, which are antibonding, and one 4 pi, which again is antibonding. Out of 6 electrons, you can see that they fill nicely up just our bonding orbitals and no electrons in antibonding orbitals, which is why benzene is particularly stable. So molecular orbital is particularly successful at explaining delocalized systems where previous models really have failed to be able to do that, and we can extend this theory to other aromatic compounds. Obviously, there is a huge amount of maths behind this. We're just looking at the pictures, but you can imagine the maths that underpins this is rather complicated, as we're dealing with lots of different wave functions of the atomic orbitals becoming molecular orbitals. But this allows chemists to understand the chemistry without worrying about the maths behind it.